All right, folks, so in the second part of this lab experiment after your extraction, this is where really the instrumentation piece comes in. And we're going to focus on the UV-Vis portion of the kind of quality test that we can do with caffeine. There's many ones that we can do, but we're going to pick UV because that's the instrument that we're talking about. So with the UV field, as with many of the calculations that you've seen before so far, Beer's law is going to be required. Right? A equals EBC. So we talked about the A, and the A stands for absorbance of the instrument or of the sample that you want. E is the molar absorptivity value. That is going to be the reference unique number really for that particular compound that you're analyzing. The B is the path length, and for us, these are 1 centimeter cuvettes, so it's going to be a 1 in that equation when you solve for it. And then C is going to be the concentration of the solution that gives you that absorbance. And that concentration is always in terms of molarity. So we're going to have to use this equation. Beer's law is going to be very important because what we have right now is a caffeine sample, and that caffeine sample is going to have to be made into a solution, and that solution is going to have to be ran on UV in order to get purity. So let's go and take a look at the directions and see what it tells us to do so far. So after I do the melting point, which is up here at the very top, it says, well, keep in mind, do that extra mass because you've used sun for the melting point. And then number 2 says dissolve with water. So whatever is left over in that round bottom flask, right? I've got this round bottom. I've only used a little bit for my melting point. I'm going to add a little bit of water in here, and I'm going to swirl it around, and that's going to dissolve quite a bit of the caffeine that I have. Then it says transfer that to a 100 ml volumetric flask. So we at least tell you that. And the reason is because concentrations are going to be important, and I need to be very particular with the volumes that I'm using. So volumetric pipettes and volumetric flasks are going to be very important after this point. So that little bit of solution of DI is going to be dumped into that volumetric. And then it says repeat that 2 or 3 times. So that means water, another small portion, number 2 and number 3, in that same flask that had your residue. And the reason is because not all of that was dissolved, not all of that was probably transferred, and we want to make sure that we get as much as possible out. So another second round of DI water, swish it, swirl it, pour it into the same volumetric flask. And then another small portion of DI water, swish it, turn it, rock it, make sure that it gets everything dissolved as much as possible. That portion goes into the same volumetric flask. So eventually what you'll want is everything out of here dissolved, everything transferred over, and then you're going to go up to the line with DI water, because that's what these directions say. It says dissolve with DI, transfer to 100 ml in a volumetric flask, at least 3 rinses. Now the key here is at least 3 rinses, and then dilute to the mark. So make sure that when you do dilute it to the mark, you mix that solution very well. That's very, very important in the whole entire process. Mixing and allowing things to do what they need to do. All right, so now what's going to happen here is that number 3 says, now calculate the expected concentration of your solution based on your personal mass. So what that means is that let's say that I had 45 milligrams here. Well, 45 milligrams can be converted into gram, right? I know how to do that conversion. At least I hope I know how to do that conversion, right? And then that gram is going to have to be converted over to moles. And again, I hope I know how to do that. In order for it go to gram to moles, we need to use formula weight in order to get there. And then once I have moles, I now know that I have this positioned in a 100 ml volumetric flask, or 0.1 liter, because we're after a molarity. That is the concentration unit that we're after, because that's what Beers' law is based off of. So if I'm after molarity, that is mole per liter. So I've taken the caffeine residue, I've dissolved it. I know how much was there because I dissolved it and I took a mass of it before we did it. I'm going to assume all of that was transferred over. So that milligram amount can be converted to gram pretty easily. That gram can go into mole because that's the common language that all these things talk with. And once I have mole, divide that by 0.1 because that is what we've made the solution in. So this will give me a molarity number. Now the question is, let's look at that molarity, right? That molarity could be way too strong in order to analyze, right? And the question here is, let's make sure that it's not too strong before we even go through the trouble of running it and analyzing it. So how do I know if that molarity is too big, right? Well, that's the purpose of Beers's law. So with Beers's law, what we're going to say is, well, 0.2 to 1.5, that's the absorbance that we like to run on our machines, because we know that not everything is ordered completely pure with us. And we know that when we make these solutions, everything's going to be a little bit lower. So if 0.1 is really the minimum cap on our UV absorbances, then we need to go a little bit higher because we need to prepare for that little bit lower readout due to the impurities, due to some of these complications that we might see. So that's why we always say 0.2 to 1.5. So you shouldn't go higher than 1.5. You shouldn't go lower than 0.2. And my advice to you is to make a sample that is somewhere in the middle. Right? If you try to make something that runs 1.5 and it actually goes over 1.5 by the time that you get there and read it, then you're going to have to dilute it down again. If you try to get something that's 0.2 and you go over there and you read and it's way below the calibration curve, then you're going to have to redo it. You're going to have to remake it again. So why waste your time? So pick something in the middle. Right? And I'm not telling you what to pick, but somewhere in the middle here is a 1 absorbance, right? So why not pick it? So 1 absorbance is equal to the molar absorptivity of caffeine, and you should know that because we talked about that in a previous video. So that's E, my path length is 1, and C is the concentration, and this is what I'm trying to solve for. So once I solve for Beer's law, this will tell me the concentration in terms of molarity that will give me an absorbance value of a 1 when I make it, or at least close to 1 when I make it. So now the objective here is to take this take this molarity, this concentration, and compare it to this one, what you actually made. Are they about the same? If not, which one's stronger? And if your sample is stronger, you're going to have to dilute this. So MV equals MV. So what that means is that I'll know the concentration of this stuff that I dissolved, put into my 100 ml flask. I know the concentration that's needed for a 1 absorbance, and it's up to me to figure out how to dilute that sample down in order to get to that point. So the first molarity I know, that's my original, that's my sample. The second molarity I'll know because that's my target absorbance concentration. What will give me my 1 absorbance? The V1 is what I'm solving for because I need to know how much of that. And then the V2, well, this is really up to you. How much do you want to make, right? Our cuvettes hold just like a handful of milliliters at a time, not very many at all. So, do you want to make 10 milliliters of the diluted sample? That's great. Do it. If you want to make 25, you want to make 50, that's up to you. Right? That's why this is worded the way that it is. We are letting you make that decision because you need to be comfortable making these decisions in order to prepare samples to run on instrumentation. Okay? So that's going to be the first objective here. I'm going to take the residue, I'm going to dissolve it and make a solution out of it, and I'm going to calculate the concentration that I actually have in my hand before I diluted anything. Okay. Then I'm going to use Beers's law, and you pick the absorbance that you want. I picked a 1 for this example, but if you wanted to pick a 0.75 or a 0.5 or a 1.25, then do it. I don't care. But 1 just seems nice and clean and easy to me, so I'll put 1 in there for the example. So I'm going to solve Beer's law, and I'm going to get the target concentration. That's what we call this. a target concentration that I need to make. That is going to give me a sample that runs close to a 1 absorbance in my case, because that's the number I picked, on the machine. And then, finally, number 3, use the dilution equation. Because I almost guarantee you this is going to be way too strong, maybe, depending on how much you isolated. So that concentration is going to have to get diluted. So this is my original. I need to go down to this concentration to Beers' law. So M1 and M2. How much V1 of this should I use? My original. And you pick the volume. You want to make 10 mils, 25 mils, 50 mils, whatever the case is, do it. Go for it. And then that will allow me to prepare a sample that will run on scale with the UV-Vis. All right? So that's going to be the next part, and that's this sample preparation for our UV-Vis instrument. Next up is this category that says, okay, standard preparation now. So just one sample is not going to do me any good. I need to build a calibration curve. If I'm going to do proper quantitative work, I need a calibration curve out of this thing. So now it's going to say, all right, well, using that same concept, take this molar absorptivity value and take target absorbance ranges and make a set of standards that are appropriate to run on a UV-Vis and make a cal curve with it. All right, so I use the same kind of concept. I have Beers' law, A equals EBC, and I get to pick the range of whatever absorbances that I want to make as long as they fall in that realm of 0.2 to 1.5. So you pick them, all right? So 1.5, maybe a 1, maybe a 0.75, maybe a 0.5, maybe a 0.25. I don't know what you want. You pick those values. That's the magic of all of this, right? All right, so what this is going to do now is, all right, I want a 1.5 absorbance. So here's my molar absorptivity. I know that value because I've looked it up in a textbook. My path length is going to be 1, and this will allow me to solve for the concentration, which is the molarity of what I need to make in order to run a standard that will give me a 1.5 absorbance or something close to it. Now, I will almost guarantee you that if you try to make that standard, and you're like, okay, well, that's my strength. That's how strong I need to make that standard with. So let me use the molarity formula to give me moles over liter. And let's say that I want to make 100 mils of that standard, right? Maybe. So that's okay. So whatever value that I get here, that's the value that I'm going to use for my molarity equation. That's the strength that I need to make. So I'm going to solve for moles because that's the amount of caffeine I need to weigh out. And then with my liter, again, you pick the standard amount. You want to make 50 mils? We'll put 0.5 there. You want to make 100 mils? We'll put 1.1 here. Right? You do that. You do you. So when we solve for this, we're going to solve for moles, and then we're going to have to use formula weight of caffeine in order to figure out grams, and then we probably need to measure out that many grams. The problem is what if this is too tiny, right? What if that's too small of an amount? Like little bitty tiny milligrams, I am not comfortable weighing that out and transferring it and feeling really good about it. So very often we will make a more concentrated version of it. When we make a more concentrated version, it's very easy to kind of shift the decimal over once and then make it 10 times too strong and then go to a 1 to 10 mil dilution in order to get this very highest standard that I would start with. All right. So again, I'm going to leave that up to you. You make those judgment calls. You call the shots on the standard prep, but that is the process that we go through in the very beginning. So use Beers' law, figure out the concentration that you should not go over. That will be your highest standard. All right. Then from there, figure out a way to make a caffeine standard that will be that concentration. And I will guarantee you that if you use this molarity, because it's going to be so low, in the molarity equation, Even if you make 100 mils of this stuff, this is going to be a very, very tiny amount. So you're going to have to go stronger and then dilute it down in order to get what you want. But that's okay, because what will happen is that you will use Beers's law for every one of these. The 1, the 0.75, the 0.5, the 0.25, and you'll get target concentrations that you will need to get those absorbances. So by doing this stronger solution, what you can then do is use that one to go and make everything else from, or everything else with. All right. So make this 10 times concentrate, and then using that one, make the rest of your calibration standards. So what you're going to see on the Excel spreadsheet when you figure out this dilution scheme is here on the bottom of that tab, it says UV data. Up here at the very top, it's going to say, all right, well, how much standard caffeine did you weigh out, right? So this is making that original standard with how much caffeine stock that we ordered did you weigh out onto a balance? How did you dilute it? This person decided to dilute it in 50 mils. What was the concentration in terms of molarity? And then what was that kind of target concentration if you were using something like a 1 absorbance or 1.5 absorbance or a 0.5 absorbance, whatever the case is? Again, that's on you. All right. Again, I would recommend 1 absorbance because it's the easiest. All right. So next up would be, all right, well, here are the target concentrations that I'm after for this particular person. That's what they decided to make. They picked absorbance values that gave them a set of standards. When they used that in Beers's law, these were the molarities that they were after. That's what they wanted. So how many mils of this concentrated caffeine standard did they use, and how did they dilute it down to? What was their total volume? And what you're seeing here is that they're using 0.1s to 0.4 mils down to 10 mils in total. Again, that's on you. Your dilution scheme and your standard preps will be different depending on what you choose to make and how much of it to make. Once those standards got prepped and fully mixed, those standards got analyzed on a UV, including a blank, and we get absorbance values for those. That blank and those concentrations and absorbances get plotted into a calibration curve, and that's what you see over here to the right-hand side. That gives me a regression line and an R-squared value. That regression line is then going to be used to solve for my sample that I prepped in the previous part. So what will happen here is that concentration is plotted on the X and absorbance is plotted on the Y. So when I ran a sample, my sample, on the UV, I get an absorbance. That absorbance goes in for the Y variable, and I solve for X. X will tell me the concentration of the diluted sample that I ran, because chances are I had to dilute it in order to get it on scale. That's the calculations that you're seeing down here at the bottom. Here's the absorbance from the sample, 0.637 is what this person got. They plugged that value into the regression line and solved for X, and they got that concentration. They diluted their sample in part 1 by taking 0.447 milliliters to 10. Well, that seems kind of odd and strange, but that's what they decided to do. Again, yours will be different. And then they back diluted, MV equals MV, right? They need to know what the concentration was beforehand. When they solve for that molarity, what you can then do is say, all right, well, I took this amount of residue for this person, 0.051. I converted that to mole. They dissolved that into 100 mils, which is 0.1 liter. And this was the molarity that they should have made. And the machine is telling them, well, no, this is the molarity, 7.17 times 10 to the negative fifth. That is the molarity that you did make. And what they're doing is that they are comparing these two values together to calculate a percent purity. So what you're finding is that, sorry, I actually said that backward. So 7.17 is the molarity from the calibration curve, and then the back dilution is this 0.000117395, right? So they're taking that value after it's been corrected and back diluted, and they're saying, all right, did that get close to 0.002? Well, no. Yeah, I got a 0.00011. Okay, well, that seems kind of off. So they've taken these two values, divided them, multiplied by 100 to get a percent purity. That's what we're after. Okay? All right, so that is the second tab, and that is the second part of this lab experience. That's what you're going to see here in the next section of the lab document. It says using DI as your reference, put that into your UV, and then take one of your standards, your high standard typically, and we're going to scan it in order to get a lambda max. Once I get the lambda max, we're going to analyze all of the standards, and we're going to analyze the sample at that lambda. Everything gets analyzed at the same wavelength. We're going to build the cal curve. We're going to solve for X. We're going to correct for dilution because chances are I diluted that sample and made it weaker, so we're going to have to work backward. And then calculate the percent of the caffeine that you extracted, the purity of it at least. How good of a cleanup job did you do in your separatory funnel steps? And what kind of product did you end up with here in the very end? All right. So that's the story with the spreadsheet, and that's the story with the second part of the caffeine extraction. It seems that most people get weirded out with this standard prep, but folks, it just takes practice. That's what it does, and we're going to keep doing this over and over and over until you do a pretty good job with being comfortable with standard prep. And that's why we don't really give you directions verbatim about how many meals to do, how much volume to make. We want you to make these judgment calls because we need you to critically think on the standard preparation and the sample preparation that goes through this process of UV-Vis analysis. All right. So good luck in the lab. There's a little insight of the calculation, a little insight into the spreadsheet, how this thing is ordered, how this thing is made. So if you've got questions, you know how to get a hold of us. You know where to find us. Come and get us. We'll kind of help you through if you need it. All right. So good luck, and we'll see you in the lab.